I'm Steve Mann and this is Paper Classroom. Welcome to another one of our video tutorials. This is in the Fibres module of the Level 2 Technical Certificate in Papermaking. And in this particular module we're going to be talking about fibres and where do they actually come from. All the clues in that picture there, so we'll get down into it. They come from nature. So paper makers don't make fibres, nature makes fibres. And this is how it does it. The seed sprouts, you get the two little pilot leaves, and from that moment on, the way is set. The plant breathes in carbon dioxide through its leaves, it sucks up water through its roots, and there's a catalytic reaction goes on that's happens with the chlorophyll and light, and the carbon dioxide and the water come together to produce molecules of glucose. And as you can see here, there's also some excess oxygen that's released into the atmosphere. So plants are really very good for us. Anything green is very good for us because it takes in carbon dioxide and it breathes out oxygen. So if all the green plants and trees in the world died, we would die very shortly afterwards because there'd be nothing to breathe oxygen. It's also a symbiotic relationship between us and plants because we take in that oxygen and we breathe out the oxygen that the carbon dioxide that the plants need. Anyway, back onto the paper making track. The plant breathes in carbon dioxide, it takes in water, and it produces glucose. Now, most of you have heard of glucose. It's a sugar. There are many, many sugars in the world. There's glucose, there's fructose, there's lactose, there's sucrose, many, probably hundreds of sugars. This makes one specific one called glucose. And this is what the glucose molecule looks like. It's a six-membered ring. So 1, 2, 3, 4, 5 carbons and an oxygen, a six-membered ring. And the most important thing to note is all these hydroxyl groups. So one here, one there, that's 2, one there, that's 3, one there, that's 4, one there, that's 5. So every single glucose molecule has 5 hydroxyl groups. And there are millions of them in a single fibre. And the hydroxyl groups are important because, as we've seen in an earlier video when we talked about hydrogen bonding in the science unit, it was the hydroxyl groups on one fibre associated with the hydroxyl groups on another fibre by hydrogen bonding that causes fibres to actually glue together. Anyway, carry on. So here is a glucose molecule. Now, the plant is almost like a little factory. It takes in carbon dioxide, it takes in water, and it produces loads and loads of glucose. And this is where the plant gets really clever. It then builds up these glucose units into what we call long chains or polymers. And it can do it in different ways. If it does it in one way, it will produce starch, and starch is the energy store for the plant. So it does store starch in some of its leaves, but if you think about a potato as an example, a plant will create a huge storage of starch in its root in the form of a potato. So if the plant wants to store energy for the future, it makes starch and then stores it somewhere. On the other hand, it can also produce what we're really interested in, which is cellulose. Now, the cellulose is the structural part of the plant. So this is the stem and the leaves. Now, starch can be fairly soluble. Cellulose is completely insoluble. So you don't want to try and make a plant structure out of starch, because when it rains it'll all dissolve and it'll have to start again. So Starch is the energy store of the plant. Cellulose is the structural building blocks of the plant. So one of the things we need to understand is, how are they different? Well, this is what a starch molecule looks like. You may recognise these, we've just seen these. I've drawn it in a different way, but these are glucose units. So here's 4 in a long chain of maybe several hundred. And if you notice, all of them are absolutely identical. On this first corner here, we've got that group, same group there, same group there, same group there. On this corner, we've got the oxygen. On this corner, we've got the OH group. I'm just sure there are other OH groups. I've just removed the clutter so you can see what's going on. That's what a starch molecule looks like. Everything is organised in the same way. Now, this is a cellulose molecule. Now, this is those exact same glucose molecules, but you'll notice that this one has been flipped and this one here has been flipped. So the only difference between starch and cellulose is the fact that in starch all the molecules are ordered in exactly the same way, and in cellulose every alternate molecule has been flipped. Now here's a little light-hearted way I often show my students when I do face-to-face teaching. Imagine elephants at the circus that used to be. They all used to go around a ring in the circus, the trunk of one elephant holding the tail of the elephant in front. Everything in exactly the same way, just like starch is in the same way. And what you never saw in the circus was this, where we flip every elephant around. So these two are holding trunks, these two are holding tails, these two are holding trunks again. So that's like a cellulose molecule. Every alternate one is flipped. So we put these things together, hopefully this makes sense. All in the same line, all in the same line, starch. Flipped, flipped, cellulose. Now that's such a tiny change really. Chemical composition absolutely identical. And again, one of the things I taught to my students was it's a bit like building a driveway out of bricks. Every brick is absolutely identical, but how you put them together will decide whether you get a good driveway or a poor driveway. If we look at the two configurations on the right here, those bricks and these bricks, if you made a driveway like that, you won't have run your car over it very often and the bricks will start to separate and come apart. On the other hand, if you look at these two patterns on the left, if you make a driveway like that, you can drive on and off it for years and they will not come apart because the pattern is different. They're interlocked. So it's not the base unit that's important, it's how you put them together. So just go back. So this is starch. It's like having those bricks not interlocked. If you put this in water, warm it up, it will dissolve. It's a very weak structure. This one here, this is like the interlocked bricks. If you put this in water, you can boil it for a week and it won't dissolve because it's cellulose. It's structurally different, which makes a huge difference to things like its solubility. Now what nature does then is it takes these chains of molecules. One ring on its own is a glucose molecule. When we string a lot of them together, we then have what we call a cellulose chain. What nature then does is it wraps a few of those cellulose chains around each other to make it stronger. and we call that structure a microfibril. What nature then? So that may be one of these. There's yellow here. So we've mixed many cellulose chains together. We've now got a microfibril. And what nature does then is it brings some microfibrils and wraps them around each other. And that makes a fibril. And the fibrils then build up to become one layer, just one layer in a fibre. And then all the layers build up to become a wall. And as we'll see later, there are 4 walls in any fibre that's not man-made. Just before we move away from this, I'll just show you what I usually do, what I usually demonstrate in my face-to-face classes. So this is a piece of rope, but it's an excellent example of how fibres work. So nature brings together carbon dioxide and water, produces glucose units. The plant strings all these glucose units together, sometimes thousands long, to make what we call a chain. And that is cellulose. So you may not see it on this camera, but that there will be something like one chain of cellulose that nature makes. It comes apart very easily. So nature understands that one chain of cellulose is not very strong. So what it does is it wraps lots of chains of cellulose around each other like this. This is what we then call the microfibril. And then just because nature's careful and likes to be doubly sure, it wraps all these microfibrils together to make an even stronger structure. And this is then called a fibril. And what happens then is the fibrils lie side by side like this, and this forms one layer in one of the walls of the fibre. These layers build up to form a complete wall, and then the walls build up to form a complete fibre. So that takes care of exactly how a fibre is constructed and where it comes from. But where do we find these fibres? Well, there are 5 places you tend to find these sort of fibres. This one there is, you find them in seed hair from the cotton plant. The cotton plant produces seed hairs of varying lengths. If it's longer than about 8 millimetres, those are taken off to the textile industry. They're woven into cotton thread and then made into textiles. If it's less than 8 millimetres long, it's not really suitable. And so the paper industry buy it, and we use those cotton linters, as they're called. And 8 millimetres is absolutely giant for us, because typically nearly all our fibres are either hardwood or softwood. A typical softwood fibre is approximately 4 millimetres long. A typical hardwood fibre is 2 millimetres long. So a cotton fibre, 8 millimetres long, huge. Another place we find fibres is in what we call the bast layer. It's in things like flax and hemp, rami, quite a few plants. And if you imagine a stalk growing in the field like this is the stalk. It's got a very, very thin layer of bark on the outside of the plants, which we don't want. We can get rid of that. It has this pithy centre that runs up the middle. We don't want that. But underneath the bark and wrapped around this pithy centre is all this fibrous material. And that layer between the bark and the pithy centre is what we call the bast. And that's where all the useful fibres are. We find some fibres in some types of grasses. This here is a type of grass used for printing in the old days. In modern days, it's used in cigarette paper. It's called esparto. So this is about the shortest fibre that we ever use in paper making. It's just 1.1 millimetres long. In the olden days, there were many mills in the UK devoted to making paper from esparto. Because the fibres were so short, it gave a paper that was absolutely beautiful appearance, wonderful formation, fantastic to print on. But as the printing became faster and faster, the forces on the paper became greater and greater. And because the esparto fibre was so short, it couldn't cope with it and it started to tear at the higher printing speeds. So they had to abandon esparto and use other longer fibres that produced a stronger paper, even though the appearance wasn't as good. So today, one of the main uses of esparto is in cigarette paper. It's used to hold open the structure of the cigarette paper to create porosity, which in turn creates or controls the burn rate of the cigarette, one of the factors. Then we also find it in certain leaves. So this here is the abaca plant. Looks very much like a banana plant. And these are the fibres that are extracted from those leaves. These can typically be, well, these are groups of fibres obviously, but a typical abaca fibre is between 8 and 12 millimetres long, so huge. These sort of fibres are used in very specialist papers, things like tea bag, where the grammage is so light, you need a very long fibre to give you the strength because it is so light. So abaca and sisal are the two preferred long fibres. And there's stem fibres, so-called stem fibres, where we use the whole of the stem, or virtually the whole of the stem, not the bark. And this is trees, and probably 95% of all paper making fibres will come from trees. They will be wood fibres. And while we're on the topic of wood fibre, one of the things that you'll need to know is just a little bit about the construction of a tree, the way that a tree is built up. A tree actually has 5 layers. The place where the tree cells are formed is here, the cambium, and the fibres the cells either move this way to become bark, or eventually they move that way, and eventually they all become heartwood. So you need to know these 5 layers: the outer bark, the phloem, the cambium, the sapwood, and the heartwood. So you would need to be able to label a diagram, given one like that, and you need to know the purposes of each of these 5 layers. Now the bark, this layer here, that's there to give physical and biological protection to the tree. This is the phloem. Cells that go here will eventually become bark. This is the cambium. As I said a moment ago, this is where all the cell division takes place, and cells either move this way to become phloem and then bark, or they move this way to become sapwood, which will eventually become heartwood. So the purpose of the sapwood is to conduct water and nutrients up and down the trunk of the tree. and the heartwood is there to give it structural strength. Well, thank you for watching this video. I hope you found it interesting. I certainly found it interesting making it. So please enjoy our other videos. Please feel free to give us any feedback. I have been taking note of your other feedbacks, and we are going to get a better microphone.